Welcome to Wisdom Docs. Tonight, settle in. Let the lights go low and let your shoulders come down from wherever they have crept up to over the course of the day. There is nothing you need to hold on to for the next little while. There is nothing you need to solve, nothing you need to remember, nothing you need to do but breathe slowly and let a very old story carry you somewhere quiet and far away. Tonight we are going looking for a mountain that no one could find for 700 years. Imagine for a moment two of the coldest, stillest places on the surface of the Earth. One is in the far north, on the great frozen dome of Greenland, where the ice lies thousands of years deep and the wind moves across the white in long, patient breaths. The other is at the very bottom of the world, in the heart of Antarctica, where the snow has been falling and settling and compressing for longer than any human memory could ever reach. These two places sit almost as far apart as it is possible to be and still be on the same planet. They have never met. They never will. And yet, buried deep inside each of them, frozen and waiting in the dark, there lies a record of the very same day. Not a photograph, not a written page, something stranger than that, and in its own way more honest, because the ice cannot lie and the ice does not forget. What lies frozen at both poles is a thin layer of sulfur, a faint chemical whisper, a fingerprint of something that happened in the sky a very long time ago. And when scientists finally drilled down through the ice and pulled up the long, pale cores, layer by layer, year by year, like reading the pages of a book that was written in frozen water, they found something that stopped them. In a single band of that ancient ice, both in the north and in the south, the sulfur did not merely rise. It surged, it spiked, it climbed higher than anything else in the entire record. How long a record? Hold this gently, because it is one of those numbers that is hard to feel and easy to let slip past. Across the last 7,000 years of ice, across the whole long span of human civilization, from the first cities to the last, there is no volcanic sulfur spike larger than this one. 7,000 years. The pyramids of Egypt, the rise and fall of empires, the entire written history of our species, and across all of it, the single greatest mark left in the ice by an exploding mountain belongs to this one event. To put that into something you can almost hold in your hand, think of Tambora. Perhaps you've heard the name. In the year 1815, a volcano called Tambora, also in Indonesia, erupted with such force that the following year became known across the world as the year without a summer. Crops failed, snow fell in June, frost killed harvests in places that had never known it. It is, for the people who study these things, one of the great benchmarks of catastrophe, the ruler against which other eruptions are measured. And this older event, this mystery, frozen in the polar ice, was bigger. Somewhere between 2 and 8 times bigger, depending on exactly how the ice is read. Larger than the year without a summer, larger than anything in 7,000 years. So there it sat in the cores from both poles, plain as anything to the people who knew how to look. A giant eruption, one of the largest in the entire history of human civilization. The Earth itself had recorded it, kept the receipt, filed it away in the deep ice where it could not be lost. And here is the part that has kept turning in my mind, the part that makes this not just a story about a volcano, but a story about a mystery. For 700 years, nobody knew which mountain made it. Think about that for just a moment as you lie there. The crime was obvious. The evidence was overwhelming. The scar was written into the ice at the top and the bottom of the world, screaming across the centuries that something enormous had happened. And yet the culprit was missing. There was no name, no place, no mountain anyone could point to and say, there, that one, that is the one that did it. The largest eruption in 7,000 years of human history, and for 7 centuries it was a crime without a suspect, a catastrophe without an address. That is the story we are going to wander into tonight. Slowly, gently, with all the time in the world, because there is no hurry here, and there never was. This is a cold case in the truest sense of the words, solved at last in the cold ice itself, and we are going to follow it from the very first faint clue to the moment, 700 years later, when someone finally stood at the rim of the wound and said, "Here, this is where it happened. This is the mountain that chilled the world." Before we go deeper, let me ask you something. And it is the kind of question I genuinely like to think about as we begin one of these long nights together. Where in the world are you listening from tonight? Whatever corner of the earth you are resting in, whatever the weather is doing outside your window, I would love to know. If you feel moved to leave a word in the comments before you drift off, I read them. And there is something quietly lovely about imagining all of us scattered across the same planet, listening to the same old story in the dark. And if you are new here, and you would like more slow journeys like this one, the kind made for the hour when the day is finally letting go of you, you are very welcome to subscribe and stay a while. There is no rush. Settle in. Let us begin the descent. Now, let us go back to that ice, because the ice is where this whole mystery starts, and the ice has more to tell us than just that something happened. The ice can tell us roughly where. This is the first clue, and it is a beautiful one, the kind of thing that feels like magic until you understand it, and then feels like magic still. The sulfur spike was not found in only one place. It was found at both poles. In the far north of Greenland, in cores with names like GISP2, drilled deep into the summit of the ice sheet, and in later records from places called NEEM and Crete, the spike is there. And in the far south, in Antarctica, in cores drawn up from the deep ice with their own quiet names, EPICA, Dome C, Dome Fuji, WAIS Divide, the very same spike is there too. North and south, top of the world and bottom of the world, the same chemical signature frozen into both. And here is why that matters so much, and why it is the very first thing that begins to narrow the search. The way the sky carries this kind of volcanic sulfur around the planet is not random. When a volcano erupts gently or even fairly violently, but not catastrophically, its sulfur stays low, drifts a little, falls back to Earth fairly close to home, and never travels very far. But when an eruption is truly colossal, when it punches its gases high enough and with enough force, the sulfur rises into the stratosphere, the high, calm, layered part of the atmosphere far above the weather, and once it is up there, it gets caught in the great slow rivers of stratospheric air that circle the planet. Now picture the whole spinning Earth for a moment. Picture the way the air moves at its highest levels. If a giant eruption happens far to the north, near the pole, its sulfur tends to spread mostly across the northern half of the world and struggle to cross over to the southern half. The same is true in reverse for an eruption far to the south. The equator acts a little like a watershed in the sky, a dividing line that high-altitude air does not easily cross. So a polar eruption leaves its mark mainly in its own hemisphere. But an eruption right on the belt of the world, near the equator, in the tropics, is different. From the middle of the planet, the high air carries the sulfur both ways at once, north and south, spreading it across both hemispheres until it eventually settles out and falls, snowing down onto the ice at both poles. So when scientists found that this enormous spike was recorded equally clearly at both ends of the Earth, in Greenland and in Antarctica together, the ice was telling them something very specific. It was telling them where to look, not the far north, not the far south, the tropics. The volcano they were hunting sat somewhere along the warm belt of the world, near the equator, between the two hemispheres it had both scarred. Let that settle for a moment, because it really is a small wonder. Long before anyone knew the name of the mountain, before they knew the island or the country, or even the rough corner of the globe, the frozen sulfur at the two poles had already handed them a clue, quietly, patiently. It said, look near the middle, look where the world is warm. The volcano you want injected its breath so high and so hard that the whole sky carried it to both ends of the earth, and that alone tells you it stood upon the equator. The ice knew the latitude of the killer long before anyone knew its name. This is the kind of thing I find so soothing about a mystery like this lying here in the quiet. The clues are not shouting, they are not flashing, they are just there, frozen and patient, waiting century after century for someone to learn how to read them. The Earth had written down the answer. It simply took us a very long time to learn the alphabet. So now we know a little more. We know an eruption happened. We know it was the largest in 7,000 years. We know from the two-pole fingerprint in the ice that it sat somewhere on the tropical belt of the planet. But knowing it was huge is one thing, and feeling how huge is another. So let us slow down even further and try to sit quietly with the scale of this thing, not to frighten ourselves because there is nothing here to fear. It happened long, long ago, and the world has long since healed its sky. But to feel the size of what the ice was remembering. There is a scale that volcanologists use to talk about the size of eruptions. It is called the Volcanic Explosivity Index, and you can think of it simply as a kind of measuring stick for how big an eruption is, running from the small and gentle at the bottom up to the world-changing at the top. Each step up the scale is not a small step. Each one is a leap, roughly tenfold. The way each step on certain scientific scales means 10 times more than the one below. And on this scale, this mystery eruption sits at level 7, VI7. The category that the people who study these things describe with the word supercolossal. Supercolossal. It is a heavy phrase and it earns its weight. An eruption of this size is not a once-in-a-lifetime event. It is not even a once-in-a-century event. On average, across the whole long history of the planet, a VEI7 eruption happens only once or twice in 1,000 years. Once or twice in 1,000 years. Most of human history passes without one. Whole civilizations rise and fall and never see anything close. This was one of those rare, enormous events that the Earth produces only a handful of times across a millennium. And it happened, and almost no one in the wider world ever knew where. Let me try to give you something more solid to hold, an image instead of a number. When this volcano erupted, it threw out something on the order of 40 cubic kilometers of solid rock, measured as what scientists call dense rock equivalent, which is simply a way of imagining all the frothy, scattered ash and pumice squeezed back down into solid stone so you can compare it fairly. 40 cubic kilometers of solid rock. Imagine a great cube of mountain 10 kilometers on a side would be far too large, so picture instead a slab of solid stone several kilometers across in every direction, lifted whole out of the body of a mountain and hurled into the sky. And remember, that is the compressed figure. The actual loose ash and pumice and shattered rock that fell across the land was many times larger in volume than that. Tens upon tens of cubic kilometers of debris, blanketing everything for enormous distances around. And then there is the sulfur itself, the very thing the ice recorded, the chemical breath of the mountain that spread to both poles. The amount of sulfur this eruption lofted into the high atmosphere is estimated at somewhere between 100 and 270 teragrams. A teragram is a unit you will likely never have used in conversation, and there is no reason you should have. It is simply a way of naming an almost unimaginable weight. 1 teragram is 1,000,000 tons. 1,000,000 tons. So this eruption lifted somewhere between 100 million and 270 million tons of sulfurous material high into the sky, where it could spread and reflect the sunlight and dim the world. The reason the estimate has a range, why it is not one tidy number, is itself a small and gentle thing to know. The figure depends on which ice core you read and how you calibrate it, how you translate the thickness of that frozen sulfur band into a weight of gas in the ancient sky. Different cores, drilled in different places, settle the number a little differently, and honest science keeps the range rather than pretending to a false precision. So we say, somewhere between 100 and 270 teragrams, somewhere between roughly 2 and 8 times the Great Tambora. An enormous world-shading exhalation, the largest the ice has recorded across the whole span of human civilization. For all of this, for all its size and all its consequence, the eruption did not even have a proper name for a very long time. The people who studied the ice cores, who saw the spike and knew it for what it was, took to calling it simply the mystery eruption. The mystery eruption. There is something almost tender about that, isn't there? A catastrophe so large it dwarfed every other in 7,000 years, and the best name anyone could give it for decades was a confession of ignorancy. The mystery eruption, the big one nobody could place, the crime everyone could see and no one could solve. And here is where the mystery truly deepens, where the long, slow heart of this story really begins to beat, because it was not as though no one tried to solve it. Far from it. For decades, as the evidence in the ice grew clearer and clearer, scientists went hunting. They knew roughly when it happened. They knew from the two-pole fingerprint roughly where, somewhere in the tropics. And they began to work through the suspects, the great tropical volcanoes that might have been capable of such a thing, trying to match each one to the crime. And one by one, the suspects failed. There was Quilotoa in the high Andes of Ecuador, a volcano that left behind a beautiful caldera now filled with a green and blue lake. For a time it was a candidate, a real eruption, a real scar, sitting at a plausible place on the tropical belt. But when the timing was checked, and the chemistry of its ash was examined, and the sheer magnitude required was weighed against what Quilotoa had actually done, it did not fit. Close perhaps in one respect or another, but not in all of them at once. The date was not quite right, or the chemical fingerprint did not match, or the size fell short. And a suspect that fails on even one count is not your culprit. So Quilotoa was set aside. There was El Chichon in Mexico, a volcano that did erupt with real violence and did loft sulfur high. It too was considered. It too was measured against the evidence in the ice. And it too fell away because while it had been a significant eruption, it had not been a super-colossal one, not on the scale the ice demanded, not the largest in 7,000 years. The sulfur did not match. The magnitude did not match. El Chichon was a real event, but it was not this event. Another suspect set gently aside, and there was Tarawera, in New Zealand, part of a volcanic region sometimes called Okataina, a place with a long and dramatic history of eruption. For a while it too found its way onto the list of the accused, but New Zealand sits well to the south of the equator, not on the tropical belt, and a volcano there would have struggled to leave its sulfur so evenly at both poles. The geography was wrong, the fingerprint was wrong, and so Tarawera too was crossed off the list. This is the shape of the mystery in those long decades before it was solved. A parade of suspects, each one brought in, examined, questioned, and released. Quilotoa, El Chichon, Tarawera, and the volcanoes of Okataina, and others besides. Each one matched the crime in some way, in timing or in place or in scale, and each one failed to match it in every way at once. That was the cruel difficulty of it. The true culprit had to satisfy 3 demands simultaneously. It had to have erupted at exactly the right moment in the 13th century. It had to sit on the tropical belt so its sulfur could reach both poles. And it had to be enormous, super-colossal, the largest in 7,000 years. Many volcanoes could meet one or two of those conditions. None of the usual suspects could meet all three. And so the years passed, and then the decades, and the mystery eruption kept its secret. The ice held the evidence. The poles held the fingerprint. The Earth, north and south, remembered the day in perfect chemical detail. And still no one could put a name to the mountain. The largest eruption in the whole history of human civilization remained, astonishingly, an unsolved case, a catastrophe that had chilled the world and left its mark at both ends of the planet, and for 700 years it stayed faceless, nameless, a giant in the dark whose footprints were everywhere and whose body was nowhere to be found. Lie with that for a little while in the quiet. There is something strangely peaceful about it, I think, when the lights are low and the day is behind you. A mystery this old, this large, and this patient. It is not a mystery that needs solving tonight. It waited 7 centuries. It is in no hurry, and neither are we. The sulfur is still there in the ice, north and south, exactly as it was, waiting in the cold and the dark the way it has waited all along. But the suspects were not the only thread anyone could pull. The ice could tell us the year and the latitude, and it could rule out the wrong mountains, but the ice alone could never quite walk us all the way to the right one. For that, the searchers would need more than chemistry. They would need the sky itself to have left its testimony in the rings of ancient trees and in the strange dimmed light that medieval eyes once looked up and saw and could not explain. They would need to understand how a mountain on the far side of the world could reach across an entire planet and cool it, and how that cooling could be read year by frozen year in the wood of trees that were alive when it happened. Because that is the next part of the wonder, and we will come to it slowly. This eruption did not simply leave a chemical mark in faraway ice and then fall silent. It changed the very light of the world for a time. It dimmed the sun, it cooled the summers, it reached out from one small island on the tropical belt and laid a cold hand across whole continents, and the living world felt it and recorded it in ways that had nothing to do with ice cores at all. The trees wrote it down in their rings, the chroniclers wrote it down in their books, though they had no idea what they were describing. The moon itself, hanging in the medieval sky, took on a strange and ominous color that careful eyes noted and wondered at. And so the second great clue was waiting, not at the poles, but in the warm and living lands where people grew their food and watched their skies and buried their dead. The ice told the searchers when and where, but the trees and the chronicles would tell them what it did. And to understand how a single mountain could leave its mark not only in frozen sulfur at both ends of the earth, but in the wood of trees and the words of monks and the color of the moon, we have to follow the sulfur upward, out of the mouth of the volcano, into the high, cold air, far above the weather, and watch what happens to the light of the sun when the sky itself turns hazy and pale. For now, though, let it rest. Let the image settle and grow quiet in your mind. A spike of sulfur in the ice at both poles, the largest in 7,000 years, larger than the year without a summer, supercolossal, the breadth of a mountain that sat upon the equator. A parade of innocent suspects, each questioned and released. Kilotoa, El Chichon, Tarawera. And at the center of it all, an empty chair where the culprit should be, a mystery 7 centuries deep, patient, cold, and waiting. The earth had written the whole thing down. It had simply never been read aloud. Not yet. Think about the chair for a moment longer, that empty chair where the guilty mountain should have been sitting. Investigators had the body. They had the time of death, pinned to a single year by the layers in the ice. They even had a rough sketch of the killer drawn from physical evidence, a profile that said this one was enormous, that it sat somewhere along the warm middle of the world, that it had thrown more sulfur into the sky than any eruption in 7,000 years. And yet for the longest time, no name, no face. Just a hole in the record where a volcano ought to be. The strangest part is how loudly the evidence shouted while staying so completely anonymous, because consider what the two poles together actually proved. A volcano in the far north, or one tucked away in the deep south, will dust its own hemisphere with sulfur and leave the other one clean. The winds that carry the high aerosol veil do not on their own cross the equator easily. They circle within their own half of the planet. So when the searchers found the very same sulfate spike pressed into Greenland and pressed into Antarctica, in the cores drilled at GISP2 and at NEEM and at Crete in the north, and in the cores drilled at EPICA Dome C and at Dome Fuji and at WAIS Divide in the south, all of them carrying the same enormous signature, at the same moment in time, the conclusion was almost forced upon them. A volcano that marks both ends of the Earth equally must have stood near the middle of it. It must have erupted somewhere in the tropics, somewhere along the equatorial band, where the high winds could take its breath and feed it into both hemispheres at once. The ice was not just a clock, it was a compass. It pointed, faintly but unmistakably, toward the warm waste of the world. And the size of the thing, try to hold the numbers gently, the way you would turn a heavy stone over in your hands without quite lifting it. The sulfate loading, the amount of sulfur-borne aerosol, the eruption flung into the high air, has been estimated somewhere in the range of 100 to 270 teragrams, which is to say 100 to 270 million tons, the exact figure sliding depending on which core and which calibration the scientists trust. Even at the low end, that is roughly twice what Tambora managed in 1815. At the high end, it is something closer to 8 times as much. This is why, in the quiet language of the journals, the event picked up a nickname that was almost a confession of defeat. They called it the mystery eruption, not a mountain, not a place, just a mystery, a thing known only by the wound it left. On the scale that volcanologists use to rank the violence of eruptions, the volcanic explosivity index, which runs from the gentlest stirrings up to the rarest cataclysms, this one sits at a 7. Super-colossal, the word for it. The same tier, the same dreadful company as Tambora itself. Eruptions of that magnitude come along, on average, only once or twice in 1,000 years. The bulk of rock thrown out has been reckoned at something near 40 cubic kilometers of dense rock equivalent, which is the way scientists describe the true mass of material once you strip away all the air and froth and imagine it compressed back into solid stone. 40 cubic kilometers of mountain turned to ash and pumice and flowing fire, and lifted, much of it, into a sky that carried it everywhere. A number like that does not really fit inside the mind. So let it stay a little blurred at the edges, a mountain's worth of rock, unmade in a matter of hours, and scattered across the whole turning planet. Now picture the investigators then in the years before the answer came. They knew all of this. They knew the year. They knew the tropics. They knew the staggering size, and still they could not find the volcano. So they did what any patient detective does when the profile is clear, but the suspect is missing. They began bringing in candidates one by one and holding each one up against the evidence to see if it matched. There was Quilotoa, far away in the high country of Ecuador, a volcano that had indeed produced a great eruption and left behind its own beautiful caldera lake. For a time it seemed a reasonable suspect. But when the careful work was done, the timing would not line up, or the chemistry of its ash did not match the glass found in the ice, or its magnitude fell short of the monster the cause demanded. One by one those mismatches mounted, and Kilauea was, in the end, quietly released. Not the one. There was El Chichon in Mexico, a volcano with its own violent history and its own reputation for throwing sulfur high into the air. It too was questioned, and it too failed to satisfy all three demands at once. The timing, the geochemistry, the sheer scale, these had to agree completely, and for El Chichon they did not, released as well. There was Tarawera in New Zealand and the wider Okataina volcanic field around it, a region capable of enormous eruptions, dragged in as another possible author of the global signal. And the same thing happened. Hold the suspect up against the full profile, against the year locked in the ice, against the chemical fingerprint of the glass, against the colossal magnitude written in the sulfur, and the match simply would not hold. One requirement might fit while another slipped, released. That was the cruelty and the elegance of this particular cold case. It was not enough for a volcano to be big. It was not enough for it to have erupted around the right time. It was not enough for its chemistry to be vaguely plausible. The true culprit had to satisfy every single one of those conditions together, the timing and the geochemistry and the magnitude all agreeing in the same breath, and for the longest time, no known volcano on the searchers list could do it. Each suspect failed on at least one count. Each was questioned and weighed and let go. And the empty chair stayed empty. So the parade went on, name after name, mountain after mountain, each one stepping into the light of the investigation and then stepping back out again, cleared. And all the while the evidence sat there, immovable and certain, in the ice at both ends of the earth. Something had happened, something tropical and enormous and very precisely dated, larger than any eruption in 7,000 years of human and pre-human time. The crime was beyond doubt. Only the criminal was missing, and the searchers, holding their lengthening list of innocent suspects, must have begun to wonder whether the volcano they were looking for had somehow erased itself so thoroughly that it could never be found at all, whether the mountain had not merely hidden, but vanished, whether there was, anywhere on the surface of the world, a place that still remembered what it had done. And the answer, it turns out, had been there all along. Waiting in two places at once, one of them older than any ice core, one of them younger than the eruption itself by only a generation or two. But to understand how those two records were eventually read and what they said, you first have to understand something about the nature of the eruption itself, about what it means for a column of rock and fire to punch through the atmosphere, not merely into the weather, but above the weather entirely, because that is the detail that made everything else possible. That is the mechanism by which one island in the tropical ocean became, for a few years in the middle of the 13th century, the engine of a global catastrophe. When a volcano erupts, the violence happens in a column. Superheated gas and shattered rock and molten droplets rush upward from the vent, driven by the extraordinary pressure of gases dissolved in the magma and then suddenly released. Imagine, if it helps, uncapping a bottle of something carbonated that has been shaken very hard, except that the bottle is a mountain and the liquid inside it is rock, and the force of that uncapping can crack the sky. The eruption column is what that uncapping produces. It rises because it is hotter and less dense than the air around it, the same reason that smoke climbs from a fire, and for a small eruption it might climb a few kilometers, a few tens of kilometers, before the rising material cools enough to stop and spread laterally in an umbrella shape. A large eruption goes further. A very large eruption goes much further. The Samalas eruption of 1257 was not a large eruption, it was a super-colossal one. The column that it produced is estimated to have risen somewhere in the order of 40 kilometers above the vent, with some estimates placing it as high as 40 to 43 kilometers. That number deserves a moment's quiet contemplation because the atmosphere is not all the same height. The lowest layer, the troposphere, the layer in which all weather happens, in which clouds form and rain falls and winds blow, extends to roughly 12 kilometers above sea level at equatorial latitudes. Above it sits the stratosphere, still, dry, intensely cold, home to the ozone layer, largely undisturbed by the churning dynamics below. The boundary between them is called the tropopause, and it is, for most practical purposes, the ceiling of the weather. Samalas's eruption column blew through the tropopause as though it were not there. At 40 kilometers, the column was already 3 times higher than that ceiling. It was not venting into the weather, it was venting into a different part of the atmosphere entirely, one whose properties would turn out to matter enormously. In the troposphere, particles wash out quickly, rain catches them, wet deposition pulls them to the ground within days or weeks. A volcanic eruption that stays below the tropopause is local in its effects, or at most regional. The material it injects into the air falls out before it can travel far. But in the stratosphere there is no rain, there is no wet removal. The air is thin and extremely cold and largely motionless in the vertical sense, and anything that reaches it lingers. Not for days, for years. The material Samalas injected in enormous quantities was sulfur dioxide, a colorless, sharp-smelling gas that is the signature emission of volcanic eruptions globally. Once sulfur dioxide enters the stratosphere, it reacts with water vapor in the small amounts present at that altitude to form sulfuric acid. The sulfuric acid condenses into tiny droplets, forming an aerosol, a mist of acid particles suspended in the thin stratospheric air. And those particles, each one too small to see individually, collectively do something very precise. They scatter incoming sunlight, not by much for each individual particle, but collectively across the global layer that the stratospheric circulation spreads them into. They reduce the amount of solar energy reaching the surface. They hold up a semi-transparent curtain between the Earth and the Sun. Think of it the way you might think of pulling a sheer blind across a south-facing window on a summer afternoon. The room does not go dark. Light still comes through. But the direct intensity of the beam is gone and the room is noticeably cooler, and the effect is sustained as long as the blind is there. Samalas did this to the planet, not to one room, to the planet, and the blind stayed up for years. The estimated sulfate loading from the 1257 eruption, the total mass of sulfate aerosol injected into the stratosphere, is somewhere between 100 and 270 teragrams, depending on which ice core calibration you use and how you model the conversion between the sulfur frozen in the ice and the total stratospheric burden. A teragram is 1,000,000 metric tons. To give that scale some texture, the Tambora eruption of 1815, which produced what historians called the year without a summer, which caused crop failures and famine across Europe and North America, and is commonly described as the most devastating volcanic climate event in recorded human history, is estimated to have deposited roughly 60 teragrams of sulfate aerosol into the stratosphere. The 1257 eruption deposited, by even the most conservative estimates, nearly twice that. By the less conservative ones, 4 times as much, perhaps more. The numbers carry wide uncertainty bands, as ice core numbers always do, but the direction is unambiguous. Whatever else happened in the summer of 1258, it happened under a stratospheric veil more opaque than any that had darkened a European or Asian or American sky in 7,000 years of human memory. And the ice kept that record. This is the part that requires slowing down, because the ice is not an obvious place to look for the biography of a volcanic eruption, and the path from fire to frozen archive is worth following in full. When sulfate aerosol particles eventually settle out of the stratosphere, after months, after years, they fall slowly through the atmosphere and land on surfaces all over the world, on soil, on rock, on ocean, on snow. The snow that falls on the polar ice caps accumulates over centuries and millennia, compressing slowly under its own weight into ice, and within that ice, preserved in the stratigraphic sequence of annual layers the way years are counted in tree rings, the chemical signature of whatever fell from the sky in any given year is locked. The deeper you drill, the older the year. Acidity spikes. Sharp increases in the concentration of sulfate and other acids in a particular ice layer are the volcanic fingerprint. They represent a year in which an unusual amount of sulfuric acid rained down from above. And both Greenland and Antarctica have such spikes in their records for a date corresponding to around 1257 or 1258, both poles. The spike appears independently in multiple Greenland cores, in the record from the GISP2 drill site, in records from NEEM from Crete, and independently in multiple Antarctic cores, in EPICA Dome C, in Dome Fuji, in the WAIS divide record. It is not an artifact of one core's peculiarities. It is not a local depositional anomaly. It is a global signal etched simultaneously into the ice at both ends of the world, and it is the largest such spike in the entire Holocene record. 7,000 years of ice and nothing else comes close, not even Tambora. That bipolar character is more than just a measure of scale. It is a fingerprint of latitude. The stratospheric circulation of the Earth, the slow, high-altitude movement of air above the weather, behaves differently from the troposphere's circulation below it. In the stratosphere, sulfate aerosol from a tropical or near-equatorial eruption spreads toward both poles. An eruption that occurs at high northern or high southern latitudes tends to deposit its aerosol predominantly in one hemisphere. The evidence accumulates mainly in the nearby polar record, but not the distant one. But a tropical eruption occurring near the equator, where the stratospheric transport is essentially symmetric in both directions, spreads its aerosol into both hemispheres with something approaching even-handedness. The signal ends up, over months to a couple of years, at both poles. A bipolar signal is therefore diagnostic of a tropical source. The ice cores were not merely recording that something enormous had happened. They were recording, in the language of their chemistry, where it had happened in general. They were saying equatorial, they were saying the tropics. That was a clue read not from an eyewitness account, not from a newspaper, not from any human observation at all, but from the chemical composition of polar ice drilled by scientists who were born 7 centuries after the eruption occurred. The planet, in its patient and indifferent way, had preserved the information and left it there for people with the right questions and the right tools to find. But ice alone was not enough. Ice could say when, approximately. Ice could say where, approximately. Ice could not say which mountain. For that, a different record had to be consulted, and it was a record that spoke in a different language entirely. Trees grow by adding a layer of wood each year. In the early part of the growing season, when warmth and light are plentiful, and the tree is growing quickly, the cells it produces are large and light-colored. Later in the season, growth slows, the cells become smaller and denser, and the wood darkens. The ring between one year's light wood and the next year's is visible to the naked eye, and the width of a ring and its density carry information about the growing conditions of that year. Wide rings tend to mean warm, favorable years. Narrow rings, or rings with particularly dense, dark, late wood, tend to mean years in which summer was cold or short, or both. Frost-damaged cells within a ring, cells that show the characteristic scarring of a late spring freeze, mark specific years when the temperature fell below freezing during the growing season, when conditions that should have been summer suddenly turned hostile and frigid. The trees of the Northern Hemisphere carry in their rings a detailed temperature record for the last several thousand years. Scientists, including Keith Briffa and Michael Sigel, and networks of researchers working within the pages, Past global changes consortium have spent decades cross-dating tree ring records from thousands of sites across Europe, North America, and Asia, constructing composite reconstructions of Northern Hemisphere summer temperature extending back a millennium and more. The method is painstaking. Each individual tree is noisy, responsive to local conditions, soil moisture, competition, disease, that have nothing to do with global climate, but average across enough trees from enough sites, and the local noise cancels and the global signal emerges. And in those composite records, 1258 stands out. The summer of 1258, and to some extent 1259, appears in multiple independent tree ring reconstructions as among the coldest or near coldest summers of the entire last millennium. Not just cold for a century, cold for 1,000 years. Some of those records place 1258 in the single coldest year across their full span of reconstruction. Others place it in the top 2 or 3. The precise ranking varies somewhat depending on which trees are included, which proxy calibration is used, which statistical approach is employed, and different researchers have argued over the margins. But the direction is not in dispute. Across virtually every high-quality Northern Hemisphere temperature reconstruction for the last 1,000 years, 1258 is a pronounced cold anomaly. A valley in the temperature record as sharp and distinctive as a missing tooth. That cold summer is the tree's testimony. The tree cannot tell you about Samalas. The tree cannot tell you about Lombok, or about Indonesia, or about anything that happened beyond its own growing season. But when the ice core says a massive tropical eruption injected an enormous stratospheric aerosol veil in 1257, and the tree ring from 1258 says that summer was profoundly colder than almost any other summer in 1,000 years, the two records are saying the same thing in different languages. The ice is saying the curtain went up in 1257. The tree is saying the light was dimmed in 1258. Together they are saying something blocked the sun for long enough that the growing season of 1258 was shortened and cooled in ways the trees could feel and could not forget. This is how science pins a year before it pins a place. The ice gives you the clock, the tree gives you the thermometer. What neither of them gives you, at least not by itself, is the address. That would require more work and more patience and a particular kind of careful cross-referencing that took decades of gradual refinement to achieve. And an important piece of that refinement came from a paper published not in 2013, when Samalas was identified, but 2 years later, in 2015, when a group of researchers led by Michael Siegel published a study in the journal Nature. The paper's title was precise and technical: Timing and Climate Forcing of Volcanic Eruptions for the Past 2,500 Years. Its purpose was to do something that sounds straightforward but was, in practice, extraordinarily difficult: to build a single, synchronized, internally consistent chronological timeline for volcanic signals in ice cores from both poles, extending back 2.5 millennia. The problem Siegel and his colleagues were solving had to do with dating uncertainty. Ice cores are dated by counting annual layers, and for the most recent centuries and millennia, that counting is very accurate, but not perfectly so. Over long time spans, small errors accumulate, and different cores dated independently can end up with their signals assigned to slightly different calendar years, off by a year or 2, or sometimes more, even when the signals themselves are recording the same event. This creates noise in the composite record. It makes it harder to be certain that what looks like the same eruption in Greenland and Antarctica is actually the same eruption and not two separate events that happened to look similar. And it makes the alignment between ice core records and tree ring records and written historical records uncertain in ways that matter for drawing conclusions about cause and effect. Siegel's approach was to use tree ring frost rings as independent calendar anchors. Frost rings are precisely dated. Each ring corresponds to exactly 1 year, no more, no less. and counting from the present backward is reliable in a way that layer counting deep in an ice core is not. If a volcanic signal in the ice can be matched to a frost ring in the trees, the tree ring year becomes a calendar pin for the ice, correcting any drift in the ice chronology. By systematically aligning the most prominent volcanic signals in multiple cores with the tree ring record, Siegel and colleagues were able to show that previous ice core chronologies had small but significant offsets, typically 1 to 3 years, affecting several major eruptions. When those offsets were corrected, the synchronized record showed the 1257 event in its full clarity, the largest sulfate spike of the last 2,500 years, properly dated to the year, sitting in both poles simultaneously, with the tree ring cooling anomaly of 1258 and 1259 following it precisely as you would expect if the aerosol veil reached its maximum global extent in the growing months after the eruption. The 2015 paper did not identify Samalas. That work had already been done by Lavigne and his team 2 years earlier. What it did was lock the clock. It built the framework within which the 1257 eruption could be assigned its precise place in the sequence of the last 2.5 millennia, confirming it as not merely large, but dominant. The single volcanic signal that more than any other event across the entire span of the record stands apart from everything around it. When future researchers look at that chart, sulfate concentration in ice versus calendar year, stretching from 500 years before the Common Era to the 19th century, the 1257 event is visible immediately. Everything else is smaller, everything else is shorter-lived, everything else is, in a very literal sense, in its shadow. There was a third kind of record, one older than ice cores and tree rings in some senses, and more immediate in another. It was the record written by human observers who looked up at the sky in the years following the eruption and described, without knowing what they were describing, the visible evidence of the stratospheric aerosol veil floating above them. A thick layer of sulfate aerosol in the stratosphere does things to light that are visible to the naked eye, especially around sunrise and at sunset, when sunlight strikes the atmosphere at shallow angles and has to travel through more of it. The scattering of that light by aerosol particles produces what meteorologists call a dust veil effect, extended twilights that glow longer and more colorfully than usual, hazes that seem to hang in the sky with no obvious source, a subtle dimming of the noontime sun that might be dismissed as thin, high cloud if the observer did not notice it persisting day after day for weeks and months. But the most dramatic observable effect, and the one most clearly recorded in historical documents, is what happens to the moon during a lunar eclipse when the stratosphere is thick with volcanic aerosol. A lunar eclipse occurs when the Earth passes directly between the sun and the full moon, and the moon moves into the Earth's shadow. Normally, even during a total lunar eclipse, the moon does not vanish entirely. It turns red or orange, lit by sunlight that has been refracted around the curved edge of the Earth through the atmosphere, stripped of its blue wavelengths by the long path through the air, the same process that colors sunrises and sunsets. But when the stratosphere carries an unusually heavy load of sulfate aerosol, that refracted light is scattered and absorbed more strongly than usual, and the moon darkens dramatically. In a severe case, it can be nearly invisible. The moon at total eclipse becomes not merely red but dim, brownish, barely distinguishable from the surrounding sky, or in extreme cases, not visible at all. This anomalous darkening is a well-recognized signature of a period of high stratospheric aerosol loading, and it has been used as a historical proxy for major volcanic events across centuries. Medieval observers who saw such an eclipse, or who noted an unusual dimming of the sun, or who described a sky that seemed to carry an unnameable haze through the months of 1258 and 1259, were observing the Samalas aerosol veil. They had no knowledge of what they were seeing, no context for it, no framework that could have told them that the strange quality of the light came from the residue of a catastrophic eruption on a tropical island they had never heard of. They simply described what was in front of them. Something was wrong with the sky. The light was different. The seasons were not behaving as they should. The moon, when it moved into shadow, was darker than it ought to be, and that darkness had no name. Some medieval accounts of unusual atmospheric effects in the years around 1258 have been identified by historians and scholars examining the documentary record alongside the ice core and tree ring evidence. The convergence between what the ice records and what the medieval observations suggest is not always exact. Interpreting historical descriptions of weather and celestial events is inherently uncertain, and not every chronicler who noted a cold summer was observing a volcanic consequence. But there is a coherence to the picture that accumulates across independent sources. The sky was different. The summers were colder. The harvests were failing, and the people who lived through it were recording these things as they happened because they were extraordinary, because they disrupted the expected order of the world, because the years around 1258 were unlike the years before them in ways that were alarming and that demanded some kind of accounting. What those people could not know, what the chronicles and the annals and the margin notes and the parish records could not record, was the cause. The cause was invisible in the most literal sense. It floated 40 kilometers above them in the form of tiny acid droplets that scattered the sunlight and could not be seen and did not fall and did not smell, and gave no sign of their presence except in the quality of the light and the temperature of the air and the depth of the hunger that followed when the cold summer shortened the growing season and the harvest came in thin and insufficient. The cause was a volcano on an island whose name they did not know, whose existence, for most of them, was beyond the edge of any map they had ever seen. It had happened months before the cold reached them, and a world away, and it had happened to a mountain that had, in the act of erupting, essentially erased itself. And this is perhaps the most remarkable thing about the ice and the trees and the medieval sky watching. As a combined archive, taken separately, no single one of them could tell the whole story. The ice could say something enormous and tropical happened in 1257. The trees could say 1258 was catastrophically cold. The chronicles could say the summers of that period were strange and terrible in ways their writers could feel but not explain. The lunar eclipse records could say the stratosphere was loaded with something unusual. But each of these records speaks only its own language. None of them speaks all at once. It took the slow, patient work of people who understood all of those languages to hold them up against each other and see that they were describing the same event from different angles, the same catastrophe refracted through different materials: ice, wood, parchment, the unaided human eye looking up at an unusually dark moon on a cold autumn night in 1258. That act of translation, reading the same story across multiple archives that were never meant to be read together, is what the decades of investigation were slowly building toward. The ice cores and the tree rings together could pin the year, they could confirm the scale, they could describe the effects with increasing precision as more cores were drilled, more forests sampled, more chronologies synchronized and cross-dated and refined. But the original question, with which mountain, remained open because neither ice nor tree rings can point to a place. They can say somewhere tropical, they can say enormous, they can say 1257, they cannot say here. And so the ice and the trees handed the case forward, carrying it as far as they could, and then passing it to the next set of investigators who would have to go to the field, who would have to look not at archives frozen in polar caps or encoded in annual rings of wood, but at the physical surface of the earth, where eruptions leave their deposits, and where those deposits, if the volcano was large enough, if the pyroclastic material was thick enough, if enough time had passed, and if the right questions were being asked, might still be there to be read. It was not a given that any such deposits would survive 7 centuries of tropical weathering and human activity. Volcanic ash and pumice in the humid, warm, biologically active environment of the Indonesian tropics do not remain pristine indefinitely. They weather, they erode, they are reworked by rain and river, they are buried under younger sediments, they become part of the soil. 700 years is a long time, and yet geology, patient in its own way, retains things. Large deposits, thick deposits, deposits of sufficient volume that erosion cannot remove them entirely in merely 7 centuries, leave traces. They leave outcrops, they leave the caldera, the enormous depression that collapses when the magma chamber empties and the roof of the volcano falls in on the void beneath it. They leave the lake that fills the caldera when rainwater accumulates over decades and centuries in the bowl of the collapse. They leave the shape of the landscape which carries the memory of the eruption in its topography long after the ash itself has been incorporated into the soil and the forest. And they leave the ice, even after the mountain has been transformed and the deposits have been partially erased and the landscape has grown over the old scars. The ice at both ends of the earth still holds its record. The ice does not forget, it merely waits for someone to come and read it. And somewhere on the surface of the earth, in the middle of the tropical ocean, on an island whose name was known to the inhabitants of the surrounding seas and coasts for as long as anyone in that region could remember, but whose name had not yet been connected to the sulfur frozen in the polar caps. Somewhere on that island, the evidence was waiting. The caldera was there. The deposits were there. Beneath the deposits, if the chronicle was to be believed, the remains of a kingdom were there. All of it sitting quietly in the tropical light through 6 centuries and then 7, through the slow procession of decades and generations and centuries, while on the other side of the world, in ice cores drilled in the polar dark, the signature of what had happened there sat equally patient, equally quiet, waiting for the moment when someone would finally think to put the 2 records in the same room. And there was a room far from any ice core, far from Lombok, far from the caldera lake and the buried deposits, where the consequences of that distant morning arrived without announcement, without context, and without explanation. The room was in England. The year was 1258, and the person who described what he saw in that room, and in the fields outside it and in the streets of the towns and the roads between them, was a monk named Matthew Paris, who sat at his desk in the Abbey of St Albans and wrote down what was happening around him with a thoroughness and a care that was unusual, even among the medieval chroniclers who made it their business to notice things. Matthew Paris was the kind of writer who did not simply record events, he interpreted them, and he worried about them, and he wrote with a plainness and a weight that makes his chronicle feel, even now, like the work of someone who understood that what he was watching was not ordinary. And what he was watching in 1258 was a year of extraordinary and unrelenting misery. The summer was cold, the rains came when they should not have and stayed longer than they should have. The crops failed. The harvests were thin and then thinner, and then in many places they simply did not come at all. The peasants who had planted in hope watched their fields turn to mud and standing water, and the grain that should have grown heavy and gold by August stood sparse and sodden and did not fill. He described a kind of thick and persistent overcast, a sky that did not behave the way a summer sky was supposed to behave, a quality of dimness and cold in the months that were supposed to be warm. He described the hunger that followed the failed harvest, moving from the countryside into the towns and from the towns into the larger settlements, a slow and terrible migration of want that had no remedy because the remedy, food, was precisely what the summer had failed to produce. And he described, in the particular way that careful medieval chroniclers described such things, the human cost of that failure, the bodies on the roads, the swollen numbers of the poor in the cities, the strain on institutions and charities that had never been designed to absorb a crisis of that scale. What Matthew Paris could not tell you, and what no person alive in England in 1258 could have told you, was why. He would have had explanations, or at least the explanations available to him in the intellectual and theological framework of the 13th century. God's displeasure, astrological conjunctions, the accumulated sins of the population expressing themselves in the weather and the harvest. These were not foolish explanations. Given what was known, they were the best available hypotheses for a phenomenon that had no other visible cause, because the visible cause, a volcano on an island half a world away, was not visible to anyone in England. It was not even imaginable. The connection between what had happened on Lombok in 1257 and what was happening in England in 1258 passed entirely through the atmosphere, invisibly, at an altitude of 40 kilometers, in the form of a thin veil of sulfate aerosol that Matthew Paris could not see, had no name for, and would never have associated with any earthly source, even if someone had been able to describe it to him. And yet the connection was there. It was there in the cold summer and the failed harvest and the thin grain and the bodies on the roads. It was as real as any connection between cause and effect, as direct as if the hand of the eruption had reached across the hemisphere and touched the English fields. The distance between Lombok and St Albans across the Indian Ocean and the Arabian Sea and the overland routes and the whole breadth of the continent is roughly 11,000 miles. The eruption bridged that distance in a matter of weeks through the stratospheric circulation, and the consequences arrived in England before the growing season was over, in time to ruin what remained of the summer. The mass graves at St Mary Spital, just outside the old walls of the City of London, in the area that would eventually be known as Spitalfields, are not described by Matthew Paris because they are not the kind of thing a monk at St Albans would necessarily have known about in detail. But they were there. When archaeologists excavated the site in the modern era, they found what they found, and what they found was disturbing and also, in a strange way, informative. Thousands of bodies, buried not in the individual graves that a medieval churchyard would normally contain, but in mass burial pits, long trenches in which the dead had been placed in large numbers, quickly, without the ceremonies and the careful spacing, and the individual attention that the medieval church's burial practices ordinarily demanded. The scale and the form of the burials indicated a crisis, a situation in which the dead were arriving faster than the ordinary machinery of burial could process them, in which the practical management of mortality had overridden the ritual management of it. When those burials were first discovered and first studied, the question, as it almost always is when mass graves from the medieval period come to light, was what had killed so many people in so short a time. The Black Death is the obvious hypothesis, because the Black Death killed enormous numbers of people across Europe in the 14th century and left mass burials almost everywhere it passed. But the Spitalfields graves were dated by radiocarbon analysis and by stratigraphic analysis of the layers in which they were found, not to the 14th century, but to the late 13th, and specifically to the period around 1258. The Black Death had not yet arrived in England. It would not arrive for nearly a century. These dead predated it entirely, and so the question remained open for some time. Famine was the answer, or at least the most plausible answer, and famine was eventually confirmed as the primary mechanism. The failed harvests and the cold summer and the hunger that followed, pressing hardest on the poor and the already vulnerable, as famine always does, producing a mortality crisis significant enough to require burial pits in the grounds of a hospital that had not previously needed them. But the question of what had caused the famine itself, what had caused the cold and the rain and the failed crops that produced the bodies that ended up in those pits, that question was not asked, or if it was asked, it was not answered for a very long time. The volcanic famine connection, the idea that a sulfate veil from a distant eruption had cooled the Northern Hemisphere enough in the summer of 1258 to cause the crop failures that caused the hunger that produced those graves, took shape gradually over the second half of the 20th century as the ice core evidence became clearer and the climate modeling became more sophisticated and the dendrochronological reconstructions became more precise. It is not a simple or a single-step argument. It requires you to hold in mind at once the physics of stratospheric aerosol loading and the biology of grain crops and the economics of medieval provisioning and the demography of urban poverty in 13th century England. But it holds. The evidence supports it. The timing aligns. And when you stand in front of it, when you hold the full chain, the eruption column punching 40 kilometers into the stratosphere, the aerosols spreading on the stratospheric circulation, the summer cooling that follows, the harvest failure, the famine, the graves at Spitalfields. When you hold that chain in your mind all at once, what you are holding is a single, connected event that stretches from Lombok to London and from the sky to the earth, and that passed invisibly through the world while it was happening without anyone, on any part of its path, understanding what was connecting them. That invisibility, that disconnection, is worth sitting with for a moment. In 1258, the world was not a small place. It was not connected by rapid communication or by the instantaneous flow of information that we take for granted now. A traveller from London to Lombok, had such a journey been imaginable, would have taken months or years and survived extraordinary hardship. The flows of information that connected the medieval world were slow and partial and filtered through enormous distances of time and geography. The people who died in the cold English summer of 1258 did not know that they were connected to the people who died on Lombok in the pyroclastic flows of 1257. The people who buried the dead at Spitalfields had never heard of Samalas. The people who had lived near the volcano had never heard of England, or if they had, only as the most distant and abstract rumour of a faraway place. And yet they were connected by the chemistry of the atmosphere and the physics of the stratospheric circulation, by the fact that the planet's air is shared and the planet's sun is shared, and the quantity of sunlight reaching any particular field of grain anywhere on Earth is affected by what is suspended in the atmosphere above it, regardless of where that suspension originated. The eruption of Samalas did not care about the political and commercial and cultural boundaries of the medieval world. It operated in a domain, the stratosphere, that those boundaries did not touch. It distributed its effects according to the physics of fluid dynamics and atmospheric chemistry, not according to any human geography. It is worth being honest about what we know and what we do not know in the way that the subject deserves. The evidence for the English famine of 1258 and its connection to a volcanic cooling event is strong. Matthew Paris's chronicle is clear, and it is corroborated by other English and continental records of the same period describing the same cold summer and the same harvest failure. The mass graves at St Mary Spital are real, and they date to this period. The ice core signal for 1257-1258 is the largest volcanic sulfate spike of the last 7,000 years, and the tree ring records confirm a significant cooling of the Northern Hemisphere in the summers immediately following. These things line up, and the connection is not in serious dispute. But the truly global synchrony of harvest failure, the claim that the volcanic cooling caused famine simultaneously across Europe, the Middle East, and Asia, is more complex. and deserves the honest qualification it requires. The evidence for the English and European famine is solid. The evidence that this famine extended simultaneously and equivalently across every region of the Northern Hemisphere is partly inferred from the climate forcing rather than fully documented region by region. Climate models tell us that the cooling was severe and widespread, but the specific documentary record of crop failure and famine varies in quality and completeness from region to region, and in some places the record is thin enough that we are inferring the human consequence from the physical evidence rather than reading it directly in chronicles and accounts. And then there is 1258 in the broader world, which is not only the year of the volcanic famine, it is also the year of the Mongol sack of Baghdad. In February of 1258, the forces of Hulagu Khan, the grandson of Genghis Khan, sacked the Abbasid capital, killed the caliph, destroyed an enormous amount of what was then the intellectual and cultural heart of the Islamic world, and ended a caliphate that had endured for 5 centuries. The death toll from the sack of Baghdad in 1258 was catastrophic by any measure, and the social and economic disruption that followed it across the broader region was enormous and lasting. If you look at the Middle East in 1258 and ask whether the suffering of that year was caused by a cold summer or by the armies of the Mongol Empire, the honest answer is that it is very difficult to disentangle, and that in some cases the attempt to attribute regional suffering in 1258 to the volcanic cooling is complicated and possibly confounded by this coincidence of catastrophes. The Mongol sack of Baghdad is not related to Samalas. The coincidence of dates is simply a coincidence, 2 vast catastrophes falling in the same year by the unrelated operation of human politics and geological physics. But the coincidence makes it harder to use documentary evidence of suffering in the broader Middle East in 1258 as clean evidence of the volcanic impact, and it is worth naming that complication honestly rather than simply enrolling all of 1258's misery in the story of the eruption. What the eruption is responsible for, and what can be said with genuine confidence, is the cooling of the Northern Hemisphere in the summers of 1258 and 1259. The cooling was real and it was severe. Some reconstructions place those summers among the coldest of the past 1,000 years in the Northern Hemisphere, which is a statement that deserves a moment to absorb, because it means that in a millennium of summers, the summer of 1258 was among the worst, among the coldest and darkest and most damaging to the growing things that human agriculture depended on. That is what one eruption on one island in 1 June or perhaps 1 September, the exact season is not entirely certain, accomplished simply by punching enough sulfur into the stratosphere to form a veil that intercepted a fraction of the sunlight that would otherwise have reached the fields of England and France and Germany and the Baltic and every other place where crops were growing and lives depended on the harvest. And the consequences did not end with the winter of 1258. This is where the story opens on to something larger and slower and in some ways more consequential than even the famine itself, because the 1257 eruption of Samalas is not only the largest volcanic event of the last 7,000 years measured by the sulfate signal in the polar ice, it is also considered a leading candidate for one of the triggering or intensifying events in the onset of the Little Ice Age. The long period of general cooling that settled over the Northern Hemisphere from roughly the 14th century through the mid-19th century, and that reshaped the climate of Europe and the North Atlantic in ways that left deep marks on the human societies living through it. The Little Ice Age is one of those climate events that is simultaneously well documented and genuinely complex in its causes, and it is worth being precise about the claim being made, because the overclaimed version, the assertion that the eruption of Samalas single-handedly caused the Little Ice Age, is not accurate, and accuracy matters here more than dramatic simplicity. The Little Ice Age was not the product of a single eruption. It developed over a period of centuries, and its causes include a cluster of large volcanic eruptions across the 13th, 14th and 15th centuries, of which Samalas in 1257 was the first and largest, but not the only one. A period of reduced solar activity in which the sun was producing somewhat less energy than in warmer periods before and after. And the internal dynamics of the ocean and the atmosphere, which can sustain and amplify a cooling trend long after its initial forcing has ended. The Little Ice Age was a multi-cause, multi-century phenomenon. Samalas is a leading suspect for its initiation, or at least for a significant intensification of the cooling conditions that eventually settled into it. But leading suspect is not sole cause, and the distinction matters. The mechanism by which a single volcanic eruption might contribute to a multi-century cooling period is interesting and not intuitively obvious, because the aerosol veil from an eruption does not last for centuries. The sulfate aerosols that cool the climate after a large eruption remain in the stratosphere for roughly 2 to 3 years before they settle out of the atmosphere, and the cooling they cause fades. A single eruption produces a pulse of cooling, not a sustained refrigeration. So how does one eruption, even the largest in 7,000 years, contribute to a cooling period that lasted centuries? The answer lies in sea ice and in what sea ice does once it forms. If a volcanic cooling pulse is severe enough and comes at the right moment in the seasonal cycle, it can cause an unusual expansion of sea ice in the polar regions. Sea ice, once it forms, is white, and white surfaces reflect sunlight rather than absorbing it. Open ocean, by contrast, is dark and absorbs sunlight, which warms the water. The shift from dark ocean to white ice therefore produces a change in the local energy balance, less sunlight absorbed, more reflected, that continues to cool the region even after the volcanic aerosols that triggered the initial expansion have settled out of the atmosphere. The sea ice, in other words, takes on the cooling function that the aerosol veil has relinquished, and it does so through a feedback loop that can persist and even expand over years and decades, long past the point where the eruption itself has any direct effect. This is what climate scientists call an ice albedo feedback, where albedo means the reflectivity of a surface. Albedo is the fraction of incoming sunlight that a surface bounces back into space rather than absorbing. Ice has a high albedo. Open ocean has a low albedo. The more ice there is, the more sunlight is reflected, the cooler the water beneath and around the ice stays, the more ice persists and forms, which reflects more sunlight, which cools the water further. The feedback loop can, under the right conditions, sustain a regional or even hemispheric cooling for years or decades after the initial forcing has ended. And if it is reinforced by additional volcanic eruptions, which is what happened in the 13th and 14th centuries when a cluster of large eruptions followed Samalas at intervals, the cooling can deepen and persist long enough to constitute something more than a temporary episode. Think of it this way: if you chill a glass of water suddenly and dramatically, the chill fades quickly when you remove the source of cold. But if in chilling the water you cause ice to form on the surface, and that ice floats and insulates the water beneath it and reflects the warmth above it, the ice can persist long after you have removed the original cold source. And if the cold source returns periodically, another large eruption, another reduction in solar output, the ice can grow and thicken faster than it melts until the system has shifted into a new condition that maintains itself through its own internal dynamics. That, in rough and simplified form, is what appears to have happened in the centuries following 1257. Samalas chilled the polar regions hard enough and fast enough to initiate an unusual expansion of sea ice. The sea ice persisted and expanded through the feedback loop. Additional eruptions in the following centuries reinforced the cooling. Reduced solar output contributed to it, and the combined effect sustained over long enough to reshape ocean circulation and atmospheric patterns produced the centuries-long cooling period we call the Little Ice Age. The people living through it did not call it the Little Ice Age. They had no name for it, because they had no frame for recognizing a multi-century climate shift in progress. What they experienced was a series of bad years and good years, of cold winters and cold summers and difficult harvests and occasional good ones, of glaciers advancing slowly down alpine valleys and of rivers freezing that did not ordinarily freeze. They experienced it as weather, as the ordinary and extraordinary variability of a world in which the seasons did not always cooperate with human needs. It is only in retrospect, with the long view, that scientific analysis of tree rings and ice cores and historical records provides that the period takes shape as something more coherent than a series of unconnected misfortunes. The irony sitting inside this particular story is that the same ice cores that reveal the Little Ice Age as a coherent climatic period are also the ice cores that preserve the sulfate spike from 1257, frozen 1,000 feet underground in polar glaciers that the people living through the cold centuries above would never have seen and could not have imagined. The evidence that connects the cause to the effect, the eruption, to the centuries of cooling, was present all along, suspended in the ice at both ends of the Earth, being slowly buried under the weight of subsequent winters. It waited there, in the dark and the cold, while the Little Ice Age it helped initiate unfolded above it, for centuries, until someone drilled down to find it. What this means, if you follow the chain of consequences out far enough, is that the morning when Samalas erupted, whenever that morning was in 1257, on a tropical island that had a name and a kingdom and a people who were its first and most immediate victims, that morning sent effects forward through time that reached well beyond the lives of anyone who saw the eruption, beyond the generation that buried the dead at Spitalfields, beyond the medieval world that Matthew Paris inhabited and documented, and into the centuries of the Little Ice Age that reshaped the demography and agriculture and culture of large parts of the Northern Hemisphere. The glaciers that advanced down alpine valleys in the 16th and 17th centuries, destroying farmland that had been cultivated for generations. The Thames that froze solidly enough in some winters to hold frost fairs on its ice. The harvest that failed in northern Europe in the colder decades of the 17th century and contributed to the famines and migrations and social pressures of that period. These things are not the direct consequence of the 1257 eruption in the simple and immediate way that the English harvest failure of 1258 was its direct consequence. They are the long-tail consequence, the sustained reverberation of a blow that set a system of feedbacks in motion and then receded while the feedbacks continued their work. The eruption struck once, the effect spread and compounded and persisted for centuries. It is a strange and humbling thing to consider that a single geological event, hours or days in its most violent phase, a few years in its direct atmospheric impact, could have consequences that stretched across centuries of human history, that the slow accumulation of sea ice in the decades after 1257, driven by the feedback loops that the eruption had initiated, could have contributed to conditions that were still affecting the lives of people in the 17th and 18th centuries, people who had no knowledge of Samalas and no way to connect the conditions of their winters and their harvests to something that had happened 400 or 500 years before they were born. The world does not announce its causes. It simply presents its effects and leaves the work of understanding the connections to whoever happens to come along later with the right tools and the right questions. The right tools in this case were the ice cores and the tree rings and the techniques for reading them, and the right questions were the ones that a generation of climate scientists and volcanologists and medieval historians began asking in increasing conversation with one another across the second half of the 20th century and into the 21st. The question of what had caused the summer of 1258 to be so cold, and the question of what had produced the enormous sulfate spike in the ice cores, and the question of which volcano had done it, and the question of what the long-term climate consequences of a VEI-7 eruption might be, these questions converged slowly through the accumulation of data and the development of methods and the gradual building of a scientific literature that could hold all of them at once. And the English famine of 1258, the one that Matthew Paris described with such careful and troubled attention, sat in the middle of that literature as a piece of evidence that the consequences of the ice core signal were not merely geophysical and abstract, but human and documented and specific. The bodies in the mass graves at St Mary Spital were not a statistic. They were individuals, each with a life and a name and a history that the circumstances of 1258 had ended prematurely. The connection between those graves and the sulfate spike in the GISP2 core is one of the most remarkable chains of evidence in the history of climate science. A connection between a chemical signal frozen in Greenland ice and the documented mortality of real human beings in a city that has been continuously inhabited for 2,000 years. The graves were found, the ice cores were drilled, the tree rings were measured, and the question that all of this evidence was asking, which mountain, where, and when, remained unanswered through all of this accumulation of evidence. The signal in the ice was clear and enormous. The cooling in the tree rings was clear and severe. The human consequences in the medieval chronicles were clear and documented. But the volcano that had produced all of it remained, through all of these years of evidence gathering, a blank, a force without a face, a cause without a source. The literature had given it a name, the mystery eruption, and the name, in its very plainness, captured something true about the situation. It was a mystery. And mysteries, if they are real mysteries and not simply puzzles that have not yet been approached from the right angle, have a way of persisting. This one persisted for 700 years, and the way it was eventually solved and the particular combination of evidence and method and circumstance that finally resolved it is a story for what comes next. A story that begins, as so many good solutions do, not with a single dramatic revelation, but with the patient convergence of threads that had been running separately for a very long time. The team that would eventually close this case was led by Franck Lavigne, a French volcanologist, and the work they published in 2013 in the Proceedings of the National Academy of Sciences represented something that rarely happens cleanly in science. Not a single breakthrough, but a convergence. 4 separate threads developed through different methods in different materials by different people, all arriving at the same answer. When convergence like that happens, when independent lines of inquiry meet at a single point they had not been aimed at together, it carries a particular weight. It means the answer is not an artifact of one method's limitations or one dataset's quirks. It means the thing is actually there. The first thread was the one that had been there longest, the ice cores. The sulfate signal in the Greenland and Antarctic cores had been known and measured and debated for decades. By the time Lavigne's team began their work, the chemical record was not in dispute. What was in dispute, and had been for all those years, was the source. The signal itself was extraordinarily precise in what it told you, and extraordinarily silent on the one question that mattered most. It told you the year. The seasonal layering of the ice gave you that layer by layer, like pages of a calendar pressed flat by the weight of centuries above. It told you the hemisphere. Or rather, it told you both hemispheres, which is a more specific and useful fact than it sounds, because a sulfate spike of this size appearing simultaneously in Greenland ice and in Antarctic ice, thousands of miles apart, at both ends of the Earth, could only have come from a source near the equator. A volcanic eruption far to the north would send its aerosols predominantly northward. A volcanic eruption far to the south would send them predominantly south. but a volcano sitting near the equator, close to the line, where the two great atmospheric circulation systems of the planet meet and divide, would inject its material into the stratosphere at a latitude where the winds could carry it both ways. Both poles would catch the fallout. Both poles did, so the ice was telling you equatorial. It was telling you enormous. It was telling you 1257. What it could not tell you was the name of the place. The chemistry of the sulfate offered a partial clue, in the way that the chemistry of a thing always carries some information about where it came from. Sulfate derived from volcanic eruptions has a particular isotopic signature, distinct from the sulfate that arrives in ice from sea spray or industrial processes, and within volcanic sulfate there are subtler chemical characteristics that can vary by source. But volcanic geochemistry is not like a fingerprint in the simple sense the word implies. Two volcanoes in the same tectonic setting, drawing on similar crustal materials, can produce aerosols that are difficult to distinguish with certainty. The chemistry narrowed the field. It pointed towards certain regions. It ruled out others, but it could not by itself name the mountain. What the ice cores could do, and this became the foundation for everything else, was establish the timing with extraordinary precision. When Seigel and his colleagues published their 2015 redating of the ice core chronology, the work that synchronized Greenland and Antarctic records and tied them to independently dated tree ring frost events, they locked the 1257 signal into a framework so well constrained that any proposed volcanic source would have to match it almost exactly to be credible. The ice was not soft evidence, it was the most precisely dated record available. Any candidate volcano would have to have erupted in the mid-13th century at a latitude close to the equator, at a scale large enough to deposit simultaneously the largest sulfate anomaly of the last 7,000 years in both polar caps. These were not loose criteria. The second thread was the one that required fieldwork, actual boots in actual ground. Franck Lavigne's team went to Lombok, and what they found there, in the stratigraphy of the deposits surrounding the Mount Rinjani volcanic complex, was a record written in stone and ash and compressed pumice that told a story of catastrophic violence on a scale that the landscape had not been able to conceal even after 7.5 centuries. Tephra is the generic term volcanologists use for all the fragmented material that an eruption throws into the air, the ash and pumice and rock fragments that rain down layer by layer on the land around a volcano. These layers accumulate in a sequence, each eruption leaving its own deposit, each deposit covering the ones beneath it and being covered in turn by the ones above, so that the ground itself becomes a kind of archive. A stratigraphic column is a physical library, and if you know how to read it, it tells you what happened and approximately when. The deposits around Samalas, around the wound in the landscape that the 1257 eruption had left, were extraordinary in their thickness and their extent. Close to the source, near what had once been the summit of the mountain, the tephra layers reached tens of meters deep. The eruption had not merely dusted the landscape with ash, it had buried it. Pyroclastic density currents, the most dangerous products of a large explosive eruption, dense mixtures of hot gas and fragmented rock that move across the landscape at speeds that can exceed 100 kilometers an hour, flowing down the flanks of the mountain like a terrible and rapid river of superheated material, had swept across western and central Lombok, covering the land in deposits that in places reached extraordinary depths. These flows had moved so far and so fast that they had reached the coast, they had entered the sea. The island's western margin bears the evidence of material that did not stop at the shoreline, but continued into the water, and the entry of pyroclastic material into the sea would have displaced the water violently, generating waves that carried the violence of the eruption outward in yet another direction. Ashfall extended beyond Lombok itself, drifting on the winds across the channel to Bali, the neighbouring island to the west, and further still, thinning as it went, but measurable in the sedimentary record at increasing distances from the source. The shape of the landscape now is different from what it was before 1257. Before the eruption, there was a mountain. After it, there was a hole. The caldera is the roughly 6 to 7 kilometre wide basin that formed when the eruption evacuated so much material so rapidly from the magma chamber beneath the summit that the overlying rock could no longer support itself and collapsed inward, is now filled by a lake. Segara Anak. The name, in the local language, means something close to child of the sea, and there is something quietly poetic in that name, given the circumstances. A great violence that hollowed out a mountain and left a lake where the summit had been, and the lake was named in a way that acknowledged the water filling the absence. Inside the caldera, visible from its rim, a newer cone has been growing since the old summit fell. Barujari. The volcano is not finished. The magma system that drove the 1257 eruption is still active, still restless, still building material upward from the interior. The wound left by one of the most violent explosions in the last 1,000 years of human history is now the floor of a lake. And in that lake, a new mountain is slowly rising. The stratigraphic evidence on Lombok was consistent with the scale demanded by the ice cores. The volume of deposited material, the tephra, the pumice, the consolidated pyroclastic deposits spread across the island and into the surrounding sea, was consistent with roughly 40 cubic kilometers of dense rock-equivalent material having been erupted. That is a number that requires a moment to translate into something imaginable. 40 cubic kilometers is not a quantity that ordinary experience prepares you to picture. Think of it instead as enough material to bury a large city, not merely to the rooftops, but to many times the height of the tallest buildings in it. Think of it as enough to dramatically and permanently alter the topography of a substantial island. Think of it as the kind of volume that, when erupted explosively and at sufficient speed, sends a column of fragmented rock and gas upward through the troposphere, the lowest layer of the atmosphere where weather lives, and past it into the stratosphere above, where the rules are different and the aerosols injected there can remain for years, spreading laterally across the entire planet, reflecting sunlight, cooling the surface below. The eruption column generated by Samalas is estimated to have reached approximately 40 to 43 kilometers in altitude. The boundary between the troposphere and the stratosphere, the tropopause, sits at roughly 12 to 17 kilometers above the equator, somewhat lower at the poles. Samalas's column pierced this boundary by a margin of more than 25 kilometers. Material injected at 40 kilometers altitude is well and truly in the stratosphere, above the rain and weather that would otherwise wash it out within days or weeks, and subject instead to the slow horizontal transport of stratospheric winds that can carry fine particles and sulfate aerosols around the entire globe before they eventually settle. That is the mechanism by which a single eruption on a small Indonesian island left its chemical signature simultaneously in the ice at both ends of the Earth. The column was high enough, the material was fine enough, and the eruption was large enough that the stratospheric veil it created was genuinely planetary in scale. But the stratigraphic and volcanological evidence, as compelling as it was, needed independent confirmation. A thick deposit of pyroclastic material on Lombok is consistent with a large eruption, but it does not by itself tell you which large eruption. Lombok sits in one of the most volcanically active regions on Earth, and its geological record contains evidence of many events across many thousands of years. To link the specific deposits around Samalas to the specific year 1257, the team needed to date the material directly. This is where the third thread came in. Buried within the pyroclastic deposits, sealed beneath meters of ash and compressed pumice, were the remains of trees. When the pyroclastic density currents swept down the flanks of Samalas and across the landscape of western Lombok, they moved through forests and fields and whatever settlements lay in their path, and they buried everything. Some of the trees that were buried had not burned completely before the ash sealed them. Their carbonized remains, branches, trunks, organic material that had once been living wood, were preserved in the deposits, compressed and darkened, but still present, still containing the carbon that had been fixed into the wood while the tree was alive. Radiocarbon dating works by measuring the ratio of a specific isotope of carbon, carbon-14, to the more common carbon-12 in organic material. While a tree is alive, it is constantly exchanging carbon with the atmosphere, incorporating new carbon-14 as it grows, and the ratio of carbon-14 to carbon-12 in its tissues reflects the ratio in the atmosphere at the time. When the tree dies, when it is killed by a pyroclastic flow and sealed in ash, it stops exchanging carbon with the atmosphere, and the carbon-14 it contains begins to decay at a known and measurable rate. By measuring how much carbon-14 remains in a sample and comparing that to how much would have been present at the time the organism died, you can calculate, within a range of uncertainty, when the organism stopped living. The carbonized wood from within the Samalas deposits returned calibrated radiocarbon ages consistent with the mid-13th century. The trees had been alive, and then they had not been alive, and the date of their cessation fell within a range that bracketed the year 1257 and confirmed that whatever buried them happened in approximately that period. The dating was not precise enough by itself to distinguish 1257 from 1240 or 1270. Radiocarbon dating at this timescale carries inherent uncertainties of some decades. But it was consistent. It did not contradict the ice core date. And combined with the ice core chronology, which carried its own very high precision, the two sources of dating evidence were mutually reinforcing. The ice said 1257, the charred wood said yes, that is possible, that is consistent, that is not ruled out. Convergence again. The fourth thread was the most technically delicate and the one that remains most openly debated in the scientific literature. It involves the geochemical fingerprinting of microscopic volcanic glass. When a silica-rich magma erupts explosively, it produces, among other things, volcanic glass, fragments of rapidly cooled melt that retain in their chemical composition a record of the magma's character at the moment of eruption. These glass shards can be extraordinarily small, fine enough to travel as crypto-tephra, invisible ash, tephra so dilute and so fine that it leaves no visible layer in the sediment but can be detected and extracted by careful laboratory processing. The chemical composition of volcanic glass, its ratios of silicon, aluminum, iron, magnesium, calcium, potassium, sodium, and other elements, varies between volcanic sources in ways that are sometimes distinctive enough to serve as a fingerprint. If you find a layer of crypto-tephra in an ice core, and if you can extract and analyze individual glass shards from that layer, you can compare their chemistry to the chemistry of glass from known volcanic deposits around the world and potentially identify the source. In the ice cores dated to around 1257, there are glass shards. The team compared the chemistry of these shards to the chemistry of glass from the Samalas deposits on Lombok. The comparison was supportive. The glass in the ice and the glass on Lombok were chemically similar in ways that are consistent with a common source. But Lavigne and his colleagues were careful in how they stated this. The correlation was supportive, not definitive. Distal tephra correlation, the matching of microscopic glass fragments found thousands of kilometers from a proposed source to the deposits of that source, is one of the more demanding and technically contested areas of volcanological research. The distances involved are immense, the samples are tiny. The chemistry of volcanic glass from geographically and tectonically similar settings can overlap in ways that complicate confident identification. The team reported the geochemical evidence as consistent with Samalas and supportive of the attribution, while acknowledging that it remained, in isolation, debated. It was one thread among four. And the convergence of the other three, the ice core timing, the stratigraphic deposits, the radiocarbon dates, was robust enough that the glass shard evidence functioned as corroboration rather than as the foundation of the case. 4 threads, none of them alone would have been sufficient. Together they were. The mystery eruption had a name, Samalas, of the Mount Rinjani volcanic complex on the island of Lombok, in what is now West Nusa Tenggara province in Indonesia. But there was a 5th element to the 2013 paper, and it was perhaps the most remarkable of all, because it came not from ice or ash or charred wood or microscopic glass, but from paper, or rather, from something older and more fragile than paper. The Babad Lombok is a chronicle. It is written in Old Javanese and Sasak, the languages of the region, and it was composed on palm leaves, the traditional writing medium of the Indonesian archipelago before paper became widely available. Palm leaf manuscripts are extraordinarily fragile things. The leaves dry and crack and crumble. They are vulnerable to insects, to moisture, to the simple passage of time. The survival of any palm leaf text across centuries involves, almost always, a chain of careful copying and recopying by scribes who understood that what they were preserving mattered, even when they could not have known exactly how it would come to matter. The Babad Lombok survived. It was there, preserved, legible to those who could read its script and its language, carrying within it a record of what had happened on Lombok in the mid-13th century, and what it said, what the manuscript had been saying for all those centuries, while the mystery eruption remained unsolved in the ice cores and the tree rings of the Northern Hemisphere, was this. There had been a great eruption, a catastrophic one. The kingdom of Pamatan, the capital, had been destroyed. Ash had fallen, burning material had flowed, people had died, the kingdom had been buried and abandoned. The manuscript gave the catastrophe a name. It named the volcano or the event in terms that the researchers could connect to the Rinjani complex, and it named the human cost in terms that, while not giving a number, made clear that the destruction was total. The kingdom of Pamatan was gone, its people were gone, its capital was gone. The land where it had stood was covered by volcanic deposit, and life there was not resumed in the same form it had existed before. The word for this in the history of eruptions reaches back to Pompeii, the volcanic burial of a settled, inhabited place. But the comparison to Pompeii, while vivid, needs to be held carefully. Pompeii has been excavated, its streets have been cleared, its buildings have been entered, its inhabitants, frozen in the ash in their final postures, have been studied and mourned for centuries. Pamatan has not been excavated. Its precise location has not been confirmed. It is known from the chronicle and inferred from the geology, a capital city described in a medieval manuscript that the chronicle says was covered by volcanic deposits consistent with those that Lavigne's team found across western and central Lombok. The deposits are real, the chronicle is real, is the logical inference that somewhere beneath the meters of compressed pyroclastic material that still covers parts of Lombok there lies a buried settlement, perhaps multiple settlements, perhaps the remains of the kingdom that the Babad Lombok describes, is a reasonable one. But it is an inference. Pamatan, as of the time the 2013 paper was published, remained unexcavated. The romantically powerful image of a Pompeii of the East, of intact streets and preserved artifacts waiting beneath the ash, needs to be held with the kind of care that the best science applies to its own enthusiasms. The city may be there, in some form. The ash is certainly there. What the ash contains and in what state of preservation, and whether anything like the imagined buried city remains, is a question that has not yet been answered, because the ground that would answer it has not yet been opened. What the Babad Lombok gives you in a form more direct than ice cores or glass shards or charred wood is the human dimension. The chronicle was not written by someone analyzing a climate signal or dating a deposit. It was written by someone recording from within the tradition of the affected culture what had happened to people. A kingdom existed, it had a name, it had a capital, it had a ruler. And then a mountain erupted and the kingdom ceased to exist as it had existed before, and the people who survived carried that memory forward, and someone wrote it down, and the writing survived. This is the detail that sits at the heart of what makes the 2013 paper genuinely remarkable beyond its contribution to volcanology. The convergence it described was not simply a convergence of scientific methods, it was a convergence of record types. The ice cores are a planetary record, the Earth's own archive, kept in cold darkness for centuries, chemical and physical rather than human. The Babad Lombok is a human record, a manuscript tradition, preserved through the care of scribes and the survival of institutions, linguistic and cultural rather than chemical. They had been describing the same day from 700 years of distance in languages so different from each other that no single discipline could easily read both. The volcanologists read the ice, the philologists and historians read the palm leaf manuscript, and when the right team assembled with the right combination of methods, they were able to hold both records up at once and see that they matched. The great sulfate spike in the polar ice and the great eruption in the Babad Lombok were the same event. The mystery eruption and the destruction of Pamatan were the same day. This is what 700 years of ignorance looks like when it ends, not a dramatic single moment of revelation, but a careful, methodical assembly of evidence, and then the quiet satisfaction of seeing the pieces align. The ice had known, the manuscript had known. Neither one, alone, could tell you the whole story. Together, they could. And now, sitting with all of that, sitting with the scale of what happened in 1257, with the sulfate spike that exceeded Tambora by a factor that still staggers researchers who work with these numbers, with the 40 cubic kilometers of erupted material and the 40-kilometer column, and the years of planetary cooling, and the failed harvests and the London mass graves, and the pyroclastic flows that entered the sea. It is worth pausing for a moment on what it means that this event existed and was enormous and affected human lives across an extraordinary range of geography, and yet was not, in the conventional historical sense, known. There was no eyewitness account from Lombok that reached the scholars of medieval Europe. There was no ambassador, no merchant, no traveling cleric who wrote home from the Indonesian archipelago to describe what they had seen. The world of 1257 was not connected in the ways that the world is now, and a cataclysm on a small island in the waters east of Bali was, to the people sitting in the cold, wet English summer of 1258 and wondering why their crops had failed again, not merely distant. It was entirely beyond the horizon of what they could have known. Matthew Paris, writing at St Albans, had no framework within which to place the summer's strangeness except the frameworks available to him. God's judgment, natural disorder, the signs of difficult times. He could not have known about Samalas. He did not know about Samalas. He recorded what he observed and what was reported to him, and what he observed and was reported was accurate as far as it went. Cold, rain, dearth, the suffering of the poor, the death of many. He did not know why, and the absence of a why in his account is not a failure of his chronicle. It is an honest record of the limits of what a human being in 1258 England could know about the world. And the people of Lombok, the people who survived the eruption, who carried the Babad Lombok's tradition forward, who knew exactly what had happened and where and to whom, had no mechanism by which to tell Greenland or Antarctica or the tree-lined forests of the Northern Hemisphere what they knew. Their record was local, specific, and real. And it remained local, preserved in a manuscript tradition that the wider world of science did not encounter and read in this context until the 21st century. 700 years, the time between the eruption and the 2013 paper, a period longer than the gap between the Black Death and the present day. During those 700 years, the ice cores accumulated more ice above the sulfate layer, pressing it deeper. The trees that had recorded the cold summers grew old and fell, and new trees grew from their edges and recorded other years. The manuscript was copied and recopied, its language growing more archaic with each generation of scribes, its content preserved, but its context, the context that would have connected it to a planetary climate signal, unknown to the people who kept it. The mass graves at St Mary Spital were covered by centuries of subsequent building and forgotten beneath the ground of a city that continued to grow above them, and the Segara Anak caldera filled, slowly, with rainwater and hydrothermal fluid, and the lake that formed there deepened and cleared and became, eventually, a place of remarkable beauty, a crater lake on the rim of which you can stand and look down into the water and see the reflection of the sky. None of these things knew about the others. The ice did not know about the manuscript did not know about the ice, the graves did not know about the caldera. Each was keeping its own record of the same event, in its own language, in its own medium, in its own time and place. And the event itself, the eruption of Samalas in 1257, did not know or care that it was being recorded at all. It simply happened with the indifferent violence that geological forces apply to the surfaces of planets, and the records formed around it, as records always do, because the world is full of materials that preserve the traces of events, and because some of those materials are very durable, and because human beings and the organisms that become the raw material of ice core proxies and the ice itself all have a way of inadvertently keeping accounts. What the 2013 paper did was not discover the eruption. The eruption had been in the ice cores for decades, named and measured and studied. What the paper did was close a circuit. It connected records that had been isolated from each other by distance and by disciplinary boundaries, and by the simple fact that no one had previously assembled the right combination of methods and materials and went looking in the right place. Lavigne and his team went to Lombok. They looked at the ground. They matched the ground to the ice. They read the manuscript, and the mystery eruption ceased to be a mystery. The Segara Anak caldera is still there. The lake is still there. Barujari, the young cone growing inside the old wound, is still building. The deposits that cover western and central Lombok are still there, compressed and layered, containing within them the carbonized remains of trees that were alive in 1256 and were not alive in 1258, and possibly containing, somewhere beneath the meters of pyroclastic material, the buried remnants of Pamatan. Perhaps that ground will be opened one day. Perhaps what it contains will be recoverable in some form. Perhaps the archaeology will be possible and will tell us something about the people who lived there and what their lives were like in the days before the mountain above them ended. Or perhaps the deposits are too thick and the preservation too poor and the location too uncertain, and what the Babad Lombok records will remain the fullest account of Pamatan that we will ever have. Both outcomes are possible. The ground has not yet given its answer. But the chronicle survives, and the ice survives, and the understanding we now have that these two things were describing the same day survives in the scientific literature, in the 2013 paper, in the proceedings of the National Academy of Sciences, and in every subsequent study of medieval climate and volcanic forcing that has built on that foundation. The mystery is solved in the sense that the source is named, and the mystery remains in the sense that beneath the ash there may yet be something waiting, and in the sense that the caldera lake and the growing cone inside it, and the volcanic system that drove one of the most powerful eruptions of the last 1,000 years, is still active, still present, still very much there. There is something that the great ice cores teach if you sit with them long enough. They are not dramatic instruments, they are quiet ones. They are cores of compressed ice drilled out of places so cold and so remote that the work of extracting them is itself a considerable feat, and they are stored in refrigerated archives and studied in cold laboratories by people whose work is patient and methodical and unglamorous in the way that all genuinely important scientific work tends to be. But what they contain is extraordinary. They contain the planet's own memory, layer by layer going down through the decades and the centuries and the millennia. They hold the chemical record of every major atmospheric event that left a trace in the ice, every large volcanic eruption, every shift in the carbon balance, every variation in the chemistry of the air that was sealed into the ice as it accumulated. The ice does not forget, it does not misremember, it does not editorialize. It simply preserves, and somewhere in that preserved record, sealed in a layer that formed in the winter of 1257 and 1258 and was then covered by the winter of 1258 and 1259 and then by every winter since, is the chemical signature of Samalas, the sulfate that travelled from a collapsing mountain on Lombok to both poles of the earth and was caught there and held there and waited there for 700 years and was then found by people who knew what they were looking for and who read it carefully and who went to Lombok and matched it to the ground and to the manuscript and to the charred wood in the ash, and who published what they found so that others could check it and extend it and build on it. The earth kept a record, a small island's manuscript tradition kept another. Modern science, patient and methodical and collaborative, read both of them together. And in that reading, the longest-running volcanic mystery of the last millennium quietly closed. The lake at Segara Anak is calm tonight, or something very like calm. The water in it is deep and cold and clear in the way that crater lakes sometimes are, and its surface, when the air is still, reflects the stars above it. The young cone of Barujari rises from the water near the center, dark against the night, still growing, adding its small increments to the new mountain that is slowly filling the old wound. The caldera rim stands around it all, kilometers wide, the eroded edge of what was once the summit of a mountain that does not exist anymore, that blew itself into the stratosphere in a single day in 1257 and sent its material around the world and killed a kingdom and cooled the summers of the Northern Hemisphere and filled mass graves in a city half a world away that had never heard its name. All of that is in the past, and the past does not change. What changes is our ability to read it. 700 years of records accumulated in ice and in manuscript and in charred wood and in glass, and then the right people assembled the records and read them together, and the answer came clear. That is a slow kind of revelation, but it is the kind that lasts. If you are still awake, somewhere in the world tonight, I would be glad to know where. The comments are there, and I read them. There is something quietly wonderful about knowing where, on the surface of this complicated planet, these slow stories find their listeners. And if you are new here, there are more stories of the same unhurried kind, waiting whenever you want them. But if the story has done its work, if the caldera lake and the polar ice and the palm leaf manuscript have settled into something restful behind your eyes, then you have done enough for one night. The mountain has already fallen. The mystery is already solved. The ice is already keeping its records in the dark. There is nothing left for you to hold on to tonight. Let it go. Let the slow weight of 700 years of evidence settle gently. Tie off here at the wisdom docks. The tide will wait till morning.